Kaushal, welcome you all in today's episode of Science Simplified only on Bharata First. Through this platform, we provide a unique opportunity to ask questions related to science and technology, which will be answered by the experts. Let your curiosity out and ask questions through a form whose link has been provided in the description box below. Do make use of this opportunity. Now, I would like to introduce to a science expert, Dr. T.V. Venkateshwaran, who is here with us to answer the questions sent to us by our viewers last week. Dr. T.V. Venkateshwaran is a senior scientist at Vigyan Prasar, New Delhi. He is also founder editor of India Science Wire. He writes regular columns on the developments related to science, technology, and society. So, the first question for today is:
Hello, my name is Gunjan. I am class 12 medical student and my question is, why does corpus luteum stay active throughout pregnancy and in the absence of fertilization is active only for 10 to 12 days? Thank you.
Interesting question. Let's look at this. Okay. So let's look at normal method. When the fertilization doesn't take place and when the fertilization takes place. Okay, both are normal, right? So if I look at the cycle, okay, without conception, okay, from 0 day to 28 day, which is normal period that one thinks of. Some people it may change, but assuming that. Okay, so what happens is that there are particularly hormones which is secreted. They change, they differ. Uh, for example, if I look at, for example, prostrogone, okay, this hormone, okay, in the initial period, you don't have it. Then slowly it goes up and it goes up. Okay, so then your cells remain intact, attached to there. But then when they come down, they start dying. Okay, so this is when your shedding starts, right? So this is where things happen. Okay, but when there is a conception, what happens is that similarly this proestrogen level is low, then it goes up. But because there is a conception, it continues to go up and then stay at high level. Same way, for example, there is something called human growth factor, that HCG, that also goes up. Okay, so when there is a conception, these put together ensure that these cells don't die. Okay, so that's what in the initial period, that's what happens. But then that's not the only thing that happens. After some time, when the placenta grows, okay, the the baby grows inside. Okay, the progesterone production shift from the corpus luteum to placenta. Okay, this occurs around the 7th to 9th week of gestation. Then after that, this is secreted by a different organ. But because this is secreted, then it remains intact. That's what essentially happens all through your pregnancy.
Hello, myself Palak Singh, and I'm a second year student of BCom Honors from Banaras Hindu University. My question is, as we know of the Big Bang Theory, what can we say about other theories of the origin of the universe, and which theory seems to be more precise to the truth?
Interesting. See, one of the two major competing theories about origin of universe in the recent period, with respect to science, of course, there were non-science theories like God created and all that. Leaving that aside, with respect to science, there were two important theories which were there. One is called a steady state theory. So, in the steady state theory, of course, it also says that universe expands because we have evidence for it. It says that there is a spontaneous creation of matter. Because of the spontaneous creation of matter, the amount of matter in any unit area remains same. Okay, so this is what steady state theory claims. Whereas the Big Bang model says that there was a high concentration, that is, the density was very, very high in the initial period, and the density thins as the universe expands. Okay, so basically meaning that the distance between galaxies are increasing, so which essentially means the density is coming down. Okay, that's how the Big Bang model looks at. This is a fundamentally two different view of universe. Now that we have found what is known as cosmic microwave background radiation, uh, most cosmologists believe that the steady state theory does not hold water. Okay, it does not seem to be that correct. Okay, so now there are not many takers for steady state theory, though there are some scientists still working on it, because in science, till you get lots of evidence which disproves, I mean, you keep trying whether it is correct or not. Okay, so that skepticism will continue to be in science. So from that, it happens. So first, let's understand what is this cosmic microwave background radiation. Okay, so suppose if I have a pot of hot water, okay, this hot water, let's say at 100 degrees, okay, so it will radiate, right? It will radiate. If I keep it, it will radiate. Slowly the temperature will come down, so it may become 40. Okay, still there will be radiation, but the nature of radiation earlier and the nature of radiation later, there will be a change, right? Because the temperature has come down. In the same way, suppose if the universe was very, very, very dense, then it should be very, very, very hot. Okay, so that radiation that came in the beginning of the universe should still be somewhere, right? And the radiation will not vanish, because we are talking about the universe. It should be there in the universe, right? And remember, if I look at sun, I am looking at universe 8 minutes ago, because the light takes for 8 minutes to come from sun to me. If I look at, for example, a star called Adra, Betelgeuse, I am looking at universe which was about 600, 700 years ago, because light takes so much of time to come from there. So which means if I'm looking at a galaxy which is a billion light years ago, I'm looking at universe which is billion years ago. Okay. So when you look deep into universe, you are actually looking back in time. Remember that. So which means whatever was the radiation there, that should be there now, right? Because that is what should be coming to us at this point of time. But then from the beginning of Big Bang, the radiation will not come, because it cannot penetrate. Because, like for example, sunlight, the cloud that you see is the last scattered light, right? So the last scattered light is what you see. Similarly, the last scattering happened when the matter emerged. That's around 3,80,000 years ago. Okay, so that time the universe was about 3,000 Kelvin. That is the universe which was there at that time. That radiation would be now 3 degree Kelvin. I mean, it would have been cooled to about 3 degree Kelvin. So we will see the radiation which is equivalent to about 3 degree Kelvin. That's what we see. It was accidentally actually discovered initially. Okay, initially in 1965, the cosmic background radiation was discovered accidentally. Okay, when they were testing an antenna. Okay, they were testing an antenna. They discovered this cosmic background. Then a specific spacecraft called Choubey was launched. It got a very good image of a cosmic background, which fitted with many of our ideas. Similarly, then we had even much better with WMAP satellite in 2003. Okay, so we got a better image of this background radiation. From this, we understand quite a bit of how universe expanded. Okay, so from this, what we know today is that roughly about 19 billion years ago, okay, sorry, about 13.8 billion years ago, the Big Bang took place. So after the Big Bang, roughly 10 to the power of minus 32 milliseconds. It's not even 1 second. Okay, at that point of time, the first particles like neutrons, protons, etc., came in. Okay, and the first nucleus, hydrogen, etc., formed around 200 seconds after the Big Bang. Okay, the first light, basically the first atoms got formed, and then the light got released around 3,80,000 years ago. That's what we are seeing is as cosmic microwave background at this point of time. Okay, so this is how it is. This is how we think the universe expanded with our current understanding of details that we get from. So what will happen, or what happened before Big Bang? For this, there is one theory which says that there is a cyclic universe, meaning that a Big Bang, universe expands, and then again the universe contracts, because if I throw a stone, after going to a particular height, the stone will come back, right? I mean, if I throw it less than the escape velocity. So the matter of the universe itself will have gravity, right? So the self gravity of universe itself will slow down the expansion, and then again make it contract, and then there'll be something called big crunch, like a big bang. The idea is that there'll be a big crunch, so it will crunch, and then again a big bang will happen. So it's called cycling. So it keeps on cycling. There is another idea that suppose if I throw the stone at let's say greater than the escape velocity, then the stone will keep going away from the earth, right? So in the same way, another theory says that the universe will keep on expanding. Okay, it will expand forever. That's it. So these are all various ideas. We really don't know which one is true. Then there is a very strange theory in the cosmology called as multiverse. What is this multiverse? Because we know that in quantum mechanics, there is a uncertainty, principle of uncertainty, right? So if two events can happen, why one event happened? So one of the solution to that is that the argument is that at that moment when the two events, out of the two event, one event happened, there was also another event happening, but that was in another universe. Okay, so the multiverse says that every time you make a decision, for example, you think should I have a drink or not? Okay, and say you say why not and have a drink, it becomes one universe. But there is another universe where you decided no, I don't want the drink. Okay, then it becomes another universe where the life story becomes completely different. Of course, we have no access to that universe. Okay, so this is a very strange story where one doesn't have physical proof for these things. These are all at this point of time wild claims about universe. That's where it all stands.
Good morning, sir. Myself Nishant, I'm a student, and my question to you is: what is the status of nuclear technology in India, and what is the future of nuclear technology in India, and how are thorium reactors better than uranium reactors?
Very interesting question. So first, let me explain what is this idea of Indian three-stage nuclear power plants. Okay, so this three-stage nuclear power plant envisages three types of nuclear reactor. One is pressurized heavy water reactor, which will use uranium as a fuel, and a fast breeder reactor, which will use plutonium as a, uh, uh, fuel, and then the heavy water reactor, okay, advanced heavy water reactor, which will use uh, uranium 233, but basically thorium. Okay, so in a sense, it's thorium, but not exactly thorium. I'll explain it. Okay, so the idea is that in the first stage, you use a natural uranium, you enrich it, you create a uranium fuel, you burn them in a pressurized heavy water reactor, you get power, and you also get the depleted uranium. And along with that, a part of the natural uranium is converted into plutonium. Okay, so the plutonium is coming to you as a byproduct, okay, as a waste actually, which you separate it out from the spent fuel, and then you collect the plutonium. Okay, you collect plutonium. That's what you do in the first stage. Once you have a plutonium, you can put the plutonium in fast breeder test reactors as fuel. When I put the plutonium here as fuel, it will release neutrons at particular spectrum, that is particular velocity. So what I do is that I cover this reactor with thorium. Okay, I give a thorium cover. Okay, I cover it with the thorium. So the neutron from here comes and interact with this thorium, and this thorium becomes what is known as U233, U233. Okay, so that's what you become. Of course, here also I get LCD. This is a waste product. Okay, this is a waste product from this. If I put thorium around, okay, or rather byproduct from this, if I put the thorium around, okay. So here there is nothing around, remember, but here I have around. So I get the thorium is converted into U233. Now in the state stage, I put this as fuel inside the reactor and cover it with thorium. I cover it with thorium. So then what happens? The thorium is converted into U33, okay, which I can put here, and then I can put a new thorium. So I can keep continuing this. Okay. So this is a thorium utilization for sustainable power. That's the third stage. Okay. So in the first stage, you are building inventory of plutonium. In the second stage, you are building the inventory of U233. Okay. Once you get enough U23, uranium 233, then you can go to third stage. Then once you go to third stage, you don't need these at all. Okay. By the time the lifetime of this reactors will be over, so you just close it. You need to have only this. So you put thorium and then keep running it. That's it you need. And India has a large stock of uranium. So with this available uranium, one is saying that you will be able to produce something like 1,55,000 gigawatts per year. Okay, that will be more than enough. But of course, whether we will actually produce it or not is a different issue. That is the capacity that we have. So where are we in this three stage? First stage, we are very well poised. Okay, except for this Kudangulam, all of them are power producing plants are pressurized heavy water reactor. So which means all of them are producing plutonium, which can be used in the second stage. Okay, so first stage, one can say that we have successfully crossed. So where are we in the second stage? In the second stage, it's the Indira Gandhi Center for Atomic Research in Kalpakkam, which is leading the research program for this work. Okay, so here a fast breeder test reactor has been in operation for 25 years. Okay, but this was not for producing actually electricity. This was for testing. How do you do the reactor? What kind of problems you will get, and so on and so forth. Using our 25 years of experience, we have now built a 500 megawatt prototype fast breeder reactor. It's prototype because this will be used for actually testing a 500 megawatt fast breeder reactor. Once we understand how it actually works, then we can produce more of it. Okay, so this one is called Bhavini. Okay, so this is being operated by Bhavini, a public sector undertaking of Department of Atomic Energy. This is to be soon commissioned. Okay, so one can say that we have successfully entered into the second stage. Okay, entered into the second stage. For the third stage, where we use uranium 233 as a fuel, again, a test reactor was started in 1996. Okay, it's called Kalpakkam mini reactor, so it's called as Kamini. Okay, it's a thorium, world's only thorium based reactor. It's an experimental reactor at this point of time. Okay, this reactor is having only 5 megawatt rating, but again, as I said, it's a test reactor. We want to understand how it goes. Basing on our understanding, we have created a advanced heavy water reactor, what you can call as design. The Baba Atomic Research Center has come up with this design. So in near future, you will have one more prototype of this advanced heavy water reactor soon. Okay, so soon it will be started to construct. So which means that we would also enter into the third stage. So that is the three-stage program. Why we want this three-stage program? Because uranium you have to import. We don't have enough stock. Okay, and plutonium is weapon grade material. So always people will have a doubt that you are not using for civilian purpose but for other purpose. But the moment you go to thorium, the thorium and uranium 233 are non weapon grade material. Okay, you cannot make weapons with them. So that's number one. Number two, we have large mines. I mean, minerals of thorium in this country. So which means that we will be energy independent. We will have energy security. We will not need to worry about whether the fuel will be supplied by a supplier or not. We will have it in our own country. So you will have energy security. So that's the idea. And then once you go to the thorium-based energy production, the nuclear power production cost will come down very drastically. Basically because your byproduct is your fuel, right? So the cost will come down substantially. So that's what one is hoping in the near future.
Sir, my question is related to Einstein's special theory of relativity. So I wanted to know exactly how time dilation works and how it is used in our GPS satellites. Thank you, sir.
Yeah, first let's understand special theory of relativity. Okay, suppose if there is let's say a space shuttle or a spacecraft. Okay, so on that spacecraft, on one wall there is a mirror, and in another wall there is a light source. Okay, in space there is no up and down, remember. Okay, so in one wall there is a light source, in another wall there is a mirror. Okay, and also a light source and a detector receiver. So the light goes from here, goes to the mirror and comes back. Okay, so what will be the time taken for this light to go and come back? Suppose if this height is d. Okay, if this height is d, then the light has traveled 2d distance, right? Okay, so 2d distance, and we know that light travels at the speed of c, right? So we know that the time taken will be 2d by c. Simple, right? So this is what the astronaut inside this spacecraft will measure, right? Very simple, right? Light goes up, light comes back. So the total distance travel is 2d. What is the speed at which it is traveling? C. So what will be the time taken? 2d by c. So this is simple. Okay. Now I am on Earth. I am watching this spacecraft. The spacecraft is moving. Okay, the spacecraft is moving. So when the spacecraft started, when the light started, the spacecraft was here. When the light hit the roof or the other wall, the spacecraft came here. Then when the light again reached the receiver, the spacecraft came here. So for me, the distance traveled is this plus this, right? So what is this distance? Okay, this height is d, remember. Okay, so this height is d. So what is this distance? This is a right angle triangle. Okay, so now I can find the L is, I mean, I can find that S is d square plus L square root of. That's the Pythagoras theorem. So this S I have found out. So now what is the time taken? So it is 2S by C, right? That will be the time taken according to me here. Okay, so this for me time taken will be this. But 2S is this, right? This is this, not 2D by C, right? So there is a, for me, this event took place with the gap of time t, not, okay? But for me, the two events, the light starting here, light reaching here, took place with the gap of this time difference, okay, which is different from this and which is longer because this distance is more, okay? S is more than D, S is more than D. So 2S will be more than 2D. So for me, the time taken is more. Okay. So the T naught and T, if I take it like that, T naught is less, T1 is more. Okay. So for when the light source is moving, the time between two events seems to be longer. Okay. So this is called as time dilation. Okay. So it's time dilation, right? So this alone is not the thing that works in GPS. Okay. That's a special theory of relativity. Then there is something called general theory of relativity. Under the general theory of relativity, gravitational force also changes the way the time behaves. Okay. So two things impinge on how the time behaves. One is the velocity. Okay. Time runs slow because of velocity. Second is gravity. Time runs fast because of weaker gravity. So as you go up, okay, gravity is weaker. Okay. So time runs fast because of weaker gravity. In gravity, the time runs slow. Okay, when something is moving fast, the time runs slow because of the velocity, right? So these are things that happens. So when a satellite is moving, you need to add both to correct. Okay. So how does a GPS satellite works? GPS satellite works by triangulation. I'm taking 3 satellites, and then they measure the time taken for my signal to go to them. From that, I gather that these 3 satellites, I know where the positions are. From that, I get my position. Okay. So when I do that, uh, 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 according to relativity, if I don't make changes, then my position will be wrong. Like, for example, the GPS satellite is moving at around at 20,000 kilometers away from Earth. Okay. So because of that, it will be 45.9 microseconds faster. Okay. And we have to nullify this before solving their equation. Also, because of the special relativity, they run 7.2 microseconds slower. Therefore, when I combine these two, I have to correct about 38.7 microseconds. This is for when I know the distance. Okay. So otherwise also I need to, the satellites don't travel exactly at one distance. So there is a constant dynamic calculation like this using Einstein theory. A correction needs to be done for the satellite clock to get the correct GPS position. This is what is happening. So if I look at these two effects, for example, the kinematic time dilation, basically because of the how fast it moves. Okay, something moves. Then the other is gravitational time dilation, that how far away it is from Earth, so that it has a weaker gravity. Okay, so then I can draw these two. So when I combine these two effects, I get a total time dilation. Okay. So in this total time dilation, for example, ISS, the difference in total time dilation is very small. So we don't really, I mean, it's something like a minus 10 uh, uh, um, milliseconds per day. So, okay, so it's so small that you don't uh, take into account at all. But whereas a GPS satellite is about 40 microseconds per day. So you need to take into account. Similarly, a geosynchronous satellite will also have around 48, 49 microseconds per day. Okay, so this you need to take into account. That's what is happening in a GPS satellite and Einstein's theory.
Hello everyone, this is Mehraj. I have done my bachelor's in science. Right now I am preparing for competitive exams. My question is, what are frontier technologies? What are the possible impacts of frontier technologies on developing countries like India? Thanks.
Very interesting and pertinent question for contemporary times. The international bodies, okay, as identified development bodies like UN Development Agency and all that, have identified about key 40 key emerging technologies for future. So this is what is called as frontier technologies. Okay, Some of them are digital, some of them are biotechnology, some of them are advanced material, okay, and some of them are related to energy and environment. Okay, so these technologies are classified like this. So let's look at some examples. For example, cloud computing, okay, or blockchain, okay, or big data analytics, okay. These are all digital technologies which are frontier technologies. So if I look at biotechnologies, stem cell, okay, medical and bioimaging, okay, or biocatalysis. Okay, biocatalysis is that using biological knowledge to produce chemical elements. Okay, so your chemical factories need not be polluting. Okay, synthetic biology, right? So these are all some of the biotechnologies which are frontier technology. When I look at advanced material, things like, say, for example, carbon nanotubes, graphene, which are related to nanotechnology, or nanomaterials, again, nanotechnology, okay, additive manufacturing, otherwise called as 3D printing. These are all related to advanced material. Why additive manufacturing is listed in material? Basically, because in additive manufacturing, you can create novel composites. Like, for example, a metal and ceramic, you can combine and produce metal ceramic composite materials. So many such things are possible. So okay, so that's advanced material. Now coming to energy and environment. Okay, so instead of big satellites, micro and nano satellites, precision agriculture. Okay, so this is another thing. Fuel cell. Okay, autonomous vehicles. Right. Carbon capture and storage. Right. So these are all hydrogen energy. These are all, for example, energy environment, future technologies that are listed. So 40 key emerging technologies for future. These are the 40 key. What are they expected to do? They expect to provide uh, uh, green energy, for example, new kinds of drugs, okay, power, okay, reduce carbon footprint, right? Ensure water recycling. So many of these things are possible with this new frontier technologies. So basically, the key things that one expects out of this uh, emerging technology is, one is combating climate change, because that's becoming one of the key challenge, and achieving circular economy. What is circular economy? So let's look at, for example, lithium, which we are using in our battery. If we mine, let's say, 100 grams of lithium, only 2 grams of lithium are recycled. So whenever you are mining 100 grams of lithium, after some time, 98 grams of lithium are lying around in this world as waste. Okay, the circular economy says that no, change it. If you are mining 100 grams of lithium, at least you should use it for so many cycles that finally, when you throw out something, that should be only about, let's say, 10% or 15%. Okay, so that's called as a circular economy. That circular economy is what one is looking at with some of these new technologies. Okay, so these are two major issues. So based on that, the international agencies are trying to push this. Okay, so this is what is happening with regard to these frontier technologies. And what happens to India? These are emerging technologies. So these are not already existing technologies. So which means that the intellectual property rights on these technologies are not already with, let's say, developed countries. So for a country like India, it gives opportunities for collaborative research, greenfield research, leapfrogging, meaning that we can take up to this modern technology without going through the route that the developed world took for its development. Okay, leapfrogging. So these are all opportunities that are lying with us. One of the important reason being that in India we have a good infrastructure for higher education. So generating human resource who would be able to absorb this technology or adapt to this technology or even innovate in this technology area we have potential. So if we have a right policy, right, let's say incentives, these provide opportunity for India to leapfrog and become a developed nation, or at least access to these technologies can become possible for a country like India if we plan properly.
Thank you, sir, for your insightful explanation of the questions. On this note, it's a wrap up of today's episode of Science Simplified only on Bharata First. Be scientific, be inquisitive. Please like, share, and subscribe to such amazing content on Bharata First. See you soon.